And again, this is the last of the T&Q talks of this week. So we have great pleasure to have Laura DeMarco from Harvard, and she'll be telling us about geometry of periodic points and families, where geometry is to be understood in a restricted sense of algebraic geometry, and points is to be understood in an extended sense of preperiodic.
Thank you. Thank you, Mahan, for that introduction. Thanks to all the organizers for making this such a wonderful experience. I'm really having a good time, and you've made it very easy for us. So thank you. Okay, so let me get started. Oh, my notes, very important. Okay, so I want to talk about, as Mahan said, geometry of, well, preperiodic points in families. So the setting is that of maps on projective spaces, the dynamics of a single map on projective spaces in any dimension, working over the field of complex numbers. But I'm especially interested in features of the dynamics that exist in families. So for example, we may have a parameter lambda, where lambda lives in some complex manifold. And for this talk, for the project that I'm thinking about with Myrto, we're really thinking about algebraic families of such maps. So explicitly, imagine that, say, S is some complex algebraic variety. So in fact, assume it's a quasi-projective, so not necessarily compact, complex, irreducible, algebraic variety. For the purposes of today's talk, you can just think that maybe S is the complex plane, or I mean, it can be one complex dimensional, or maybe it's a finitely punctured Riemann surface, compact Riemann surface minus finitely many points. And the family of maps will define some morphism on the product of S and Pn. So here, say, capital Phi is going to represent a map from the product to itself, which we defined by taking a parameter lambda from S and a point Z from the projective space sent to, well, the same parameter. It's fixing the parameters, and then some map that will depend holomorphically on lambda, or more specifically, algebraically. And I'm going to assume that the maps that have interesting dynamics are of degree bigger than 1. Okay, so families of maps, but parameterized algebraically in a parameter. So polynomial, the coefficients are, say, polynomial functions. Project that we're thinking about is to obtain a characterization, a complete understanding of the subvarieties, the algebraic subvarieties of the space that contain lots of periodic points or preperiodic points of phi. What is the geometry of the families of periodic points in this space? Okay, so I'm writing it here in a sort of vague way. So characterize the algebraic subvarieties, say X, inside this product space, containing many, by which I mean a Zariski dense set of preperiodic points for this family. And for those of you who are not so familiar with this language, again, what this means is that if you look, so that if you have just the set of the preperiodic points. First of all, what does that mean? In every fiber, you have lots and lots of periodic and preperiodic points. So I'm just asking that X, and of course they sometimes exist in nice families and sometimes collide and look ugly, but over every fiber you have a lot of them. And I'm just asking which subvarieties happen to cross through a lot of them. But this just means that the intersection with X is not contained in a proper algebraic subvariety of X. So not, so i.e. This is not contained in a proper algebraic subvariety of X. So if X were an algebraic curve, so one complex dimensional, then I'm asking for which such curves is this intersection infinite? So in that case, it's just finite versus infinite. Just one quick comment. I'm dealing with a family parameterized by S. So S is my parameter space. I haven't specified what kinds of subvarieties I'm looking at, but just a standing assumption, I want to assume that X surjects to S. So I have my S, I have my space, S cross Pn. So again, over each parameter lambda, I have a Pn and I have the action of a dynamical system. And I want to assume that my X is maybe some family of subvarieties over all of S. So if this is X, just for assume that the projection is surjective. Okay. Otherwise, I'll cut down the parameter space and work with a smaller parameter space. Okay, so I'm going to assume of subvarieties of Pn. Really, the language I want to assume is it's flat, but we don't need to worry about technicalities. Just assume I have some family of subvarieties over S. All right, when does it hit lots of periodic or preperiodic points? Okay, so my goal in this talk, let me just say, is to state a conjectural answer, a conjectural characterization. I do not know the answer for sure. I just want to present a conjecture and then some examples and try to explain why I think it's reasonable, why I think it's a reasonable characterization. Okay, so I'm not going to state theorems of, or nothing new in any case. But before I do that, it's important to remark that this is really a very ambitious goal, I should say. Even very special cases are already very difficult. And so just a few of those special cases I want to mention. The eraser is here. Okay, I'm going to erase the title and put some remarks here before I state the conjecture formally. Okay. Okay, so first note, suppose just for a moment that the dimension of the base is 0. That is to say, this is a single point. So I'm really just talking about one complex and a holomorphic map from Pn to Pn. Okay. Already, the characterization is not known, is essentially wide open, except in a few situations, one of which, where's Roman? Is he here? One of which will be discussed by Roman in his talk an hour from now. So already the dimension S equals 0 case is hard, very hard. So let me just say it that way. Already hard, essentially wide open. And the conjectural answer has a name. So the conjectural characterization has a name. It goes by what's called, you may have heard of, the dynamical Manin-Mumford conjecture. Roman will say more about that, I'm sure. It was just a quick remark. It was first proposed by Shouwu Zhang as in his development of studying analogies between the setting of algebraic dynamics, morphisms on algebraic varieties, and the setting of the study of algebraic abelian varieties. So the second comment I want to make, so I'm not going to say anything more about this for now. The second comment I want to make is that this includes, so the study of dynamics on Pn includes more or less the whole theory of abelian varieties. So even in the dimension s equals 0 case, this characterization, which is now actually a theorem, well, has been in the dimension equals 0 case for a good 40 years. So characterization includes, for example, the proof of what was originally called the Manin-Mumford conjecture. So it includes a theorem, for example, the celebrated result of Raynaud, which goes back, I think, to 83, although I didn't check the publication year, which characterized subvarieties, algebraic subvarieties of abelian varieties. Okay, remember, for those who are, again, not familiar with this language, an abelian variety is a complex torus, which can be embedded into a projective space. So it's the projective complex tori, that's the abelian varieties. So the characterization of the subvarieties of abelian varieties, which contain a Zariski-dense set of, well, preperiodic points for some endomorphism, are the torsion points with X intersected with the torsion points Zariski-dense. And there's a complete characterization. They're really just the subgroups or torsion translates of the subgroups. So there is a complete understanding in this case. Just a remark, again, so if this is new to you, let me explain why does this kind of discussion contain essentially the whole theory of abelian varieties? Because if you're given any abelian variety at all, you can equip it with some dynamics. Of course, we know it's a group. So for example, take the endomorphism, often denoted this way, which is multiplication by 2. You take a point and you send it to that point plus itself, 2 times the point. Okay? That endomorphism, it turns out, extends to some projective space. So there exists an embedding of A into some projective space of some dimension, so that this endomorphism extends to a morphism of projective space of the same degree. Okay? And the preperiodic points, so the torsion points here are preperiodic for phi. Yeah. Will depend on phi, absolutely. Sorry, yes, given, yeah, so I wrote it in a vague way. Given the family of dynamical systems, so given phi S, Pn, characterize the subvarieties. Absolutely, it is part of the data. It just so happens that if you start with an abelian variety, it doesn't matter which endomorphism you take, because there, if you take any of these non-trivial endomorphisms, the torsion points are precisely the preperiodic points independent of that choice. So yeah, in that case, it's really about the group structure of the abelian variety. But in general, as we know, the set of periodic points will depend very much on the map.
When n equals 1.
So when n equal, yeah, so it's a little bit different than the construction of lattice maps. So if you start with an elliptic curve, so you start with a one-dimensional abelian variety, this particular construction will embed your elliptic curve into a larger projective space. It'll be a genuine embedding. But those of us who study one-dimensional complex dynamics indeed know that in the one-dimensional case, there's an alternative way to compare preperiodic points and torsion points. One can take a quotient of the elliptic curve to P1 and induce a dynamical system in that way. And then again, in that same case, you get torsion points coincide with preperiodic. But this is a construction that would work in any dimension. The quotient version does not work in arbitrary dimension. So it's very similar to the construction of lattice, but it is not the same. Okay, so this, just to say that this question, this is in fact the way that Myrto and I came to thinking about this question in the first place, was exactly this parallel. But now, from now until the end of the talk, I really won't say anything else about abelian varieties. So if you're not familiar with that theory, that's also okay. This is just to say this is the inspiration of everything that we've been doing here. All right. And of course, I was going to set my clock so that I could keep track of how much time I've used, and I forgot to press start. So anyways, I'll go until roughly 10 o'clock, I guess. Okay, so as I said, my goal for this talk, which I'm going to do now, is to state a conjectural characterization of such subvarieties. I want to state the conjecture. I want to formulate or present some examples. Some of the examples, I should say, are not obviously in this language. So it takes some doing to translate the example to the setting of this problem. I, in fact, even surprised myself to learn that essentially every theorem that I've worked on in the last 10 or 15 years is a special case of this conjecture. I didn't even realize that myself until very recently. So certain settings, take some translation. But and then the last thing I'd like to do, if possible, well, I can tell you a little bit more of what we know about the conjecture, but I may or may not get to that. Okay, so here's the conjecture. Okay, now I keep moving the eraser around. All right, here we go. Let me erase the dimension equals 0 comments and state the conjecture here, and hopefully keep it up for the rest of the discussion. Sorry, maybe it was useful to have that. Oh well, too late. Okay, so here, this is all right, sort of an analytic formulation of the conjecture. All right, so again, the setting is that we're given this family of maps, algebraic family of maps, okay, over the field of complex numbers. S is a complex algebraic variety, as I've said, irreducible. And we're given, so we're given the dynamics. And then suppose you're given now this family of subvarieties of Pn, so a family of projective varieties, itself parameterized by S. And then I'm just going to label the two conditions 1 and 2. So the first condition is that X intersects the preperiodic points in the family in a Zariski dense subset. So there are lots and lots of them. Should be equivalent to saying that a certain current is non-zero. And so let me just write it down, and then I'll say what the notation is. Certain dynamical current wedged with itself some number of times, intersected with the current of integration on X, or restricted to X, so to speak, is non-zero. Okay. So at first glance, this is not very helpful or clarifying. I have to tell you what these symbols are, and then I'll try to give you a feel for what this is saying. This is what we believe is true. It may not be true. Okay, so what is this? So T phi here, this T hat phi is the, for those in complex dynamics will know this is the canonical green current for the family of dynamical systems. It's a positive 1,1 current, which is on the total space. So I'll write it in words, and then I'll say how it's constructed, how it is constructed. So this is, we might call a certain canonical green current for phi. It's a, as I said, it's a positive 1,1 current on the total space on this complex manifold, which is the total space. So in dimension 1, Charles actually constructed it for us already. Let me just give a quick description of how it's produced. You can start with your favorite smooth, say in positive 1-1 form, for example, the Fubini-Studi form on the projective space, just on one copy of the projective space. You can pull it back by a projection to live in the total family. So you can say, let omega, say, be the Fubini-Studi form on the projective space. I don't have notation. Let's say you have the projection just to this factor, Pn. Let's call that, say, P for projection. You pull it back. It defines a smooth 1-1 form on your total space. And then you can do iteration to produce this T phi. So then one can take, if my family of maps are of degree D, remember, I'm assuming that this degree is bigger than 1. Then you start pulling it back by the iterates, by the nth iterate, normalizing, and this sequence of forms will converge weakly to this object. And it is canonical in the sense that, well, it's characterized by its invariance under the pullback operation, at least if we work with currents that have, say, continuous potentials, nice properties, so that it's not supported on some exceptional subvariety of this space. This construction of the current, so similar to that in dimension 1, I suppose goes back to the work of Fornas and Sibony originally, as far as I understand. Just a remark, comparing it to what Charles was discussing. Of course, I'm doing this in a family. If you take this current and you wedge it with itself n times, so the dimension of the dynamical space, the fiber, if you wedge it with itself n times, this is now, one can think of this as a family of measures. So here it's a 1-1 current. You can think of it like a family of 1-1 currents over S. If you wedge it with itself n times, you can think of it as a family of measures in your fiber. And what measures are they? They're precisely the unique measures of maximal entropy in this family. Okay, so this object bundles together the measures of maximal entropy. So on fibers is that appealing now to the work of Briand and Duval, but here I'm doing this in families. Okay, so that's what this current is. So this dynamical invariant current. So this L, so for a general X, what we really want to say is that the intersection, I really want to take the top power and say the intersection with the measure of maximal entropy should be non-zero, but that's not quite the right thing to look at for a characterization. So L, let me write down the definition of L. Oh, okay. Okay, so this L, it's an integer, positive, well, not necessarily positive, a non-negative integer, which is by definition the relative dimension or the fiber dimension of the smallest invariant subvariety that contains X. I'm going to give a precise definition in a moment, but just a remark. It might be that my family of varieties is actually living inside some smaller family of dynamical systems. And so I really want to take the measures corresponding to the smaller, the family living on some smaller subvariety. So L is that dimension. So is the relative or fiber dimension of the smallest subvariety, say Y, sitting inside S cross Pn, which is, well, I should be a little careful. Either itself preperiodic for phi, so some family of subvarieties which are already their own dynamical system for phi, or one has to be a little careful, preperiodic for something that commutes with phi. And for an endomorphism, a map that commutes with phi. They're not necessarily the same family of subvarieties. So there's a slightly more technical way to say this, but I just want to emphasize what I'm doing here is to say, cut down your space. If X lives inside something that's invariant for phi, cut down to that space first. Cut down to that space first. For the sake of this talk, you can ignore this other case. Just imagine that you're going to cut down the space to something, instead of having fiber dimension n, we'll have fiber dimension L. That's what this L is. And as such, what we're doing is we're saying, then we take what is now the family of measures on that cut down space, intersecting it with X and checking whether that's possible. I want to make sure the statement more or less makes sense, even if the characterization maybe does not seem meaningful, but at least the statement, I hope the definition makes sense. So that's what this L is. All right. Okay, a few more remarks that I need to make. Oh yes. So Dean is not here, but in his talk on Tuesday, which was about currents, where he gave some nice background on currents. So I'm imagining all of you are experts on currents, and I will say nothing else about what these objects really are. And maybe it's not even so important for this talk to know what it is. It's just that such an object exists. He also made the comment, well, if you don't like currents, then ... And he gave some slide to try to describe the geometry of intersection of currents just from a geometric point of view. So if you don't like currents, there's a slightly weaker formulation of this conjecture that doesn't mention currents at all. So let me state that, so you have maybe something to hold on to. Let me erase hypothesis about S. Okay. Again, remember S could just be an algebraic. So a sort of a weaker form, though I say weaker, but I should say it's still hard and essentially and wide open, and in fact equivalent to the dynamical Manin-Mumford case when dimension of S is 0. So I'll say weaker form, but that's not really a fair word. But in the weaker form, the statement is that it's not an if and only if, but the statement is that condition 1 here, this Zariski density, implies that, well, I want to say that it implies that this measure is non-zero, but maybe you can't show that. At the very least, it should imply that the dimension of this family of varieties, the total dimension of this X in the total space, should be at least that number L. This is an LL current. So that in order to be non-zero, the dimension has to be at least L. So, but we can step back and say, well, what does this mean? So in particular, if X happens to intersect lots of periodic points, let me draw one picture. Let me add it to this picture. If X intersects lots of periodic points, okay. And as I said, also, you can assume for the sake of this talk that L and N are the same quantity. That is to say, suppose there's no invariant subvariety. So I have this family of subvarieties X. Now, for each such map, it has its Julia set, by which I mean, say, the support of its measure of maximal entropy. And it has, say, lots of repelling periodic points. Now, the periodic points themselves, they depend in some algebraic way on the parameter S. So the periodic points live in this family in some way. Maybe it defines itself some algebraic subvariety. So you have lots of periodic points. Now, the family might be messy, so these periodic points can all cross each other in a complicated way. So the statement is that, so again, okay, so for simplicity, also assume that this L is just n, the ambient dimension. This is the generic case. This is typical for a typical phi and a typical x. You can just forget about this L altogether and assume that your x is not in any periodic subvariety. Okay, so for simplicity, assume L is n. So what am I saying? I'm saying that x is just intersecting all these lots of preperiodic points of f. But how can I make that happen? The only way that should be able to happen is if the dimension of x is big enough. Notice the dimension of a single preperiodic point, if you follow it algebraically, the dimension is the same as the dimension of S, the base, sorry. The dimension of a periodic point itself is the same as S. The dimension of the total space is this S plus n. So to get intersection, you want those to be at least, at worst, complementary dimensions. Okay, so to expect intersections, you want the total, so if S is the dimension of S, you want, the dimension of X, plus this little s to be at least as big as the dimension of the total space. You want these to be not worse than complementary dimensions. And so that's really saying the same thing. You cancel out the s's if you want intersections. So for intersections to take place, to expect them to take place, you want this dimension condition. So in particular, we're saying that if you indeed have lots of intersections with those periodic points, this dimension condition should be satisfied. That's what I'm saying. And as I said, this is already very difficult to prove. This is known completely in only one setting, and that's the abelian variety setting. So it's very important for me to state that there is a recent theorem from last year. So a 2022 preprint. That the conjecture as I've formulated it, or the weaker form, the conjecture holds for phi. Let me erase now this. For phi, the extension of an endomorphism of an abelian scheme over S, a family of abelian varieties over S, where X is contained in that family of abelian varieties. And let me say that their proof involves a lot of ingredients that are not just complex analytic. There's a lot of number theory in their proof. They begin by assuming everything is defined over Q bar. They build height estimates. It involves work that was done over at least 3 decades. So this is just the sort of the last step. Height theory, so a lot of arithmetic geometry of abelian varieties, plus ingredients from model theory, specifically some works using the theory of O minimality of Pila and Wilkie, and as well as all the height estimates prior to that. It's a big process to get to this characterization for families of abelian varieties. And yet I'm hoping that with tools from complex dynamics, we might be able to nevertheless answer it in this much more general setting of complex dynamical systems. Yeah, Cheryl, you had a question. Yeah, so they prove both. So their first theorem is the weaker form, But what they actually do, and this is where our conjecture is coming from, I should say, is give a characterization in the setting of abelian varieties. But this is not the way they write their characterization. The words they use are, X therefore has what's called maximal Betti rank. But if you work through the definitions, one can deduce that it's exactly this quantity. So this reduces to the notion of, in the abelian variety case, saying X has maximal Betti rank. This current restricts to something called the Betti form on the family of abelian varieties. So that's in the abelian variety case. So here we can think of it as the analog is saying that X has maximal phi rank. So one can define the same kind of quantity using the form. And this is what Myrto and I were doing in our discussions. Yeah, Martin. Well, yes and no. Not really. But remember that, so it's actually sort of crucial for in this dimension count that I'm really dealing with a family. So if dimension were 0, so if it's just one map, the characterization, which I did not state, is that X itself has to be preperiodic. So if this were or preperiodic for something that commutes with it and blah, blah, blah. Okay. Essentially, the characterization is that X itself is preperiodic. And so in this case, because I'm dealing with a family, I don't require that X is preperiodic, but it has to be big enough inside something that is preperiodic. So S does play a role in a rather subtle way. In a rather subtle way, because of the sort of dimension count of the intersection in the top. So it was not so clear, I should say. I'm not, I wouldn't necessarily guarantee that this conjecture is true. But the one thing I do know is that 2 implies 1. Okay? So I'll maybe I'll state just, and then I'll get to examples. How am I doing? Yeah, okay, so just say it's known. The non-vanishing of this current does indeed guarantee that the preperiodic points are Zariski dense. Again, this current, which, and you take its top wedge power, is really a measure. You're really thinking, or measure in the fibers, you're really thinking about the distribution. You should think about the distribution of the repelling cycles. And so what we're saying is the fact that this measures non-zero forces intersections with those repelling cycles. And I say known as opposed to saying theorem. This is not new for me. This implication exists in the literature, though never stated in quite this language. And so one can build on some work of Roman, which was written in a very different setting in the study of bifurcation currents. It has a paper called Higher Bifurcation Currents, I think is the title. So it was written in a different setting, but if you use what he did, you can get this. He wrote it, though, for families of maps on P1. Later, Gautier extended some of what he did to families of maps on Pn, and in an article of Bertolo and Bianchi and Dupont. Yeah, these are all studying the context of stability, J stability, but the arguments will give this implication. But again, unfortunately, it's what's stated explicitly in literature doesn't quite give what we want. So you really should go back to their proofs and build on some earlier work of Dean and Sibony. Okay, so one can combine a bunch of stuff that's in the literature, write it down, and get this implication. Okay, so maybe for the proceedings that Mahan mentioned, maybe this is the right place. I should write this down. I'm in the process of writing this down, so it's clear. To emphasize that one implication is known. The reverse implication here, by the way, is false. Okay, dimension is not enough to characterize. In the case of one map where there's no S, then dimension is enough. But in general, dimension is not enough, and there are interesting counterexamples to show that I don't have time to discuss. Yeah. It could be very small, could be 0. I mean, yeah, it's okay. So I didn't give you technical hypotheses. So over a general fiber, yes, it will have constant dimension. So you can just work in that world. However, indeed, in general, of course, dimensions could pop up, and so one might want to consider only what we call flat families of subvarieties, and in particular, that would say, oh, let's just talk about the ones that are constant dimension in a fiber, and then we don't have to worry about that. Okay. So there are some technical things that one should write down to make a cleaner statement. That's right. Well, in each fiber. Yeah, it's not really a measure, but if you restrict to a fiber, it should have the right in a fiber in some appropriately invariant thing, it would restrict to a measure. Yeah, and so I'm going to ignore some things that can happen in subvarieties. But of course, if the dimension pops up in practice, if the dimension becomes maximal, then certainly I'm intersecting with lots of preperiodic. Okay, let me describe just a few examples and try to put this in some context, which is maybe a little surprising. Okay, I want to just say, okay, not only is this known, I should say this conjecture is also known when n is 1. Okay, so let me just discuss for a moment the n equals 1 case. So what does that mean? So my phi is this holomorphic or algebraic family of maps on P1, a family of rational functions, parameterized, where the coefficients, again, are some holomorphic or rational or polynomial function of some parameter. Okay, so again, I said for simplicity, assume L is the ambient dimension. So here, L could only be 0 or 1. It's just a fiber dimension of the smallest invariant thing containing X. So I'm given my X. Sorry. First of all, what is X? X is surjective onto S. So X, let me draw the picture again, and then I'll erase that one. So X, so the fibers are just a P1. So a subvariety, it's either everything, it's dominant to the base, or maybe it intersects fibers in some finite set of points. Okay, so it either intersects in points or it's the whole thing. And I don't want to take the whole thing, so let me assume it's a proper subvariety. The whole thing we already know, points are Zariski-closure. So if I have a proper subvariety, it looks something like this inside my total space, and L could be 0 or 1. Now, what does it mean for L to be 0? L to be 0 means that X itself, because it has the same dimension as dimension of S, it would mean X itself is preperiodic. So if L were 0, this means X is itself preperiodic for phi. So it's just a family of periodic or preperiodic points, persistently so. That's what L equals 0 means. L equals 1 means it's not. Okay, so there are only two options here. Either it's preperiodic persistently or it's not. So what is this conjecture saying? If it's preperiodic persistently, every point is a preperiodic point. So certainly it's Zariski dense, 1 holds. Here, L is 0. So my current wedge 0 times, this is say just the constant function 1. This disappears. And I'm left with the current of integration. which is a non-zero current. So the L equals 0 case, every point is preperiodic, and the current of integration is non-zero. Okay, so it trivially holds. So for the L equals 0 case, the conjecture holds. Both sides hold. 1 and 2 are satisfied. Vacuous. Okay, so L equals 1 is the interesting case. So the L equals 1 case means it's not preperiodic. Now, just for a moment, let me go to even further special case. Suppose X, and you'll see that you actually know about this conjecture already. Suppose X is the critical locus. Suppose X is the critical locus. In other words, these are exactly the 2D minus 2 critical points in the map. Okay, so X is parameterizing, in some sense, the family of critical points. To say L equals 1, so assume I'm in a special case. To say L equals 1 means the critical points are not persistently preperiodic in this family. What is this quantity here? This current at least if you project it down to the parameter space, is precisely the bifurcation current for this family. One can take this as the definition even. It's not the definition I originally gave, but it's a definition as formulated by Charles and Roman in one of their papers. One can take this indeed as the definition of the bifurcation current. Okay, so it's some current, positive 1,1 current that lives on the base. What is it doing? It's detecting how the critical locus intersects the measures of maximal entropy. And that's what I studied in my thesis. This current vanishes if and only if the family is stable, J stable. So equals 0 if and only if the family phi, which I'm thinking of as really a family of maps, is stable, J stable, in the sense of Lyubich and Magnier, Sade, and Sullivan. All of the maps will be topologically conjugate on their Julia sets over the whole parameter space. But remember, this is an algebraic family of maps. And so to be J stable on an entire algebraic family is very rare. And what we know from a theorem of McMullen is that the only such family is either trivial, meaning they're all conformally conjugate, they're basically the same map, or it's a lattice family. So by McMullen's theorem, I guess this was a theorem of mine in my thesis, but by McMullen's theorem, write his name, if I can squeeze it in at the bottom of the board here, by McMullen's theorem, this family is either trivial or a lattice family. Okay, but, sorry, to just comment for people who already know, the lattice family, the one coming from elliptic curves, the critical locus is preperiodic for the lattice family. So we're not in this setting. So actually, this, in our case, this doesn't even arise. I'm just going to throw that out. That would correspond to an L equals 0 case. So if I'm assuming that the critical locus is not persistently preperiodic, the only way this current can vanish is if the family is trivial. All the maps are the same map up to Möbius conjugacy. And so in particular, what do we conclude from this in the critical locus? That the vanishing of this current corresponds to stability. But that's only happening if it's trivial. And so either those critical points are periodic or they're preperiodic or they're not. And it would be the same in all fibers. It would be the same in all fibers. And I'm assuming they're not persistently preperiodic, so they're never preperiodic. So if this is vanishing, there are no preperiodic points in the family at all. And on the other hand, if it's not vanishing, Montel's theorem would tell us that there are lots of preperiodic points. In fact, lots of repelling points that hit this locus. So, in other words, in the critical locus, it boils down to some things that are known that the conjecture holds. It's related to the stability of the characterization of stability in terms of a current. That's just the case of the critical locus. And since I'm running out of time, I'll just mention the general case is very similar. If you take an arbitrary x, so it's known for all cases in dimension 1. If I take an arbitrary x, not the critical locus, just some other family of algebraic family of moving points, the same thing goes true. The current vanishes if and only if the family is trivial, or it's persistently preperiodic. And that's something I had proved some years ago. So I won't write it down, but I want to emphasize a similar idea goes through in general. It's known in all cases when n is equal to 1. For higher n, I just remark for higher n, for n bigger than 1, this case of x equals critical locus. So then it's a family of hypersurfaces.
Recording in progress.
Did we forget to start the recording, or is that just a reminder? Okay. If you take the critical locus, which is a family of hypersurfaces, I said 2 implies 1 is known, but 1 implies 2 is still open. Okay, so in higher dimensions, this is still open, even in the special case of a family of hypersurfaces, which happens to be the critical locus. Generically, the critical locus is known to be irreducible, at least in degrees bigger than 2. Okay, let me skip ahead. There's one more sort of fun example I wanted to mention, which is a special case of this conjecture, though perhaps not obviously a special case. So I'm now going to erase all of this. This was all just to say it's known when n equals 1. So I want to give one final example, which is coming from one-dimensional dynamics, but for which it corresponds to a higher n in the statement of the theorem. So it's still 1D dynamics, but n bigger than 1 as an example of conjecture. So one other setting in which, an example of a setting in which I know this statement. So here's a theorem, whoops, which is a recent result. Again, joint with, as I said, all of this was joint work with Myrto Mavraki. So again, joint with Myrto. And it's about the Mandelbrot set. So the statement is, so okay, here's my picture. Okay. Put my little baby there. Okay, the Mandelbrot set. So remember the Mandelbrot set corresponding to the family of dynamical systems, which fits into this context, family of dynamical systems. C is in the complex plane. The theorem is that, it's a weird theorem, so just bear with me here. There are only finitely many lines, say L, inside C, real lines, these are over R. There's an example of one. There are only finitely many lines, L, containing more than 2 post-critically finite parameters C. There are only finitely many lines in the complex plane, real lines in the complex plane, containing more than 2 post-critically finite parameters. Okay. So for the non-dynamics folks, if there are any non-complex dynamics folks, remember PCF, post-critically finite, means that the orbit of 0 is finite. Okay, so there are a bunch of them. Well, let me put the origin over here. So, of course, there's the centers of the hyperbolic components. And then there's this dense set of what we call the Misiurevich points in the boundary, where 0 is strictly preperiodic. There are lots and lots of them. They're dense in the boundary, as I said, of the Mandelbrot set, and then one for each of these centers of hyperbolic components. So again, if you take any pair of them, so just notice, if you take any pair, of course, you can connect them with a line. So there are lots of lines passing through 2 points. Lots of them. And there are some lines that pass through more. So for example, the real line, the real axis, has infinitely many PCF parameters. The imaginary axis has I, 0, and minus I, has at least 3. Maybe there are more, I don't know. The imaginary axis has at least 3. The real axis has infinitely many. I don't know of any other examples, and I would love to know if there are any other examples. So of course, I don't know. Is it only the real axis and the imaginary axis? I don't know. It may very well be that every single other line contains only, at most, 2 post-critically finite. By the way, one can also say, just for fun, I'll mention it, there are in fact only finitely many horizontal lines that contain more than 1 PCF point. Horizontal lines, except for the real axis, probably only contain at most 1. And we know that all but finitely many do. This funny theorem is a special case of this conjecture. So I want to take the last 2 minutes to try to at least tell you how these 2 things are related. It's okay. All right, I'll try anyways. I'll try to do it in 2, but it'll probably be impossible anyhow. I claim this theorem is actually a special case of the conjecture. Of course, I'm calling it a theorem because it's a theorem. It's actually proved. As I said, the conjecture in general is wide open, and there are only sort of little special cases that we can handle. OK, so how is this related to that? So first of all, this was a statement about real lines, identifying the complex plane with R2. So the first thing is, I said this is really a statement over the field of complex numbers. So I'd like to complexify things. So one can sort of rewrite this as a statement about lines. Let's say, suppose you start with the line, I don't know, let me just be explicit here. Suppose I start with the line ax plus by equals, let me not use c, r. So let's say a, b, and r are real numbers. So I have, this is defining a line in R2. I hope you give me that. Then we could associate to it a complex line. For example, a plus ib x plus a minus ib y equals r. So this is now a complex line in C2. So this is in R2. Now this could define a complex line in C2. And the reason I'm choosing this particular one is that if a particular parameter happens to lie on L, then C and C bar, or maybe it's the other way around, anyway, something like this is in, I don't know, this L star. So just first of all, I want to work over C. So it's convenient to translate my lines over R to lines over C. Okay? Now, that aside, once you've done that, what's the space of maps and what dynamics am I going to do? Well, not surprisingly, perhaps I'm going to talk about the dynamics of the quadratic polynomials. So my S, my parameter space, I'll do it the other eraser here. My parameter space is going to be built from the following. One looks at, let me call this V. One looks at the space of all lines. The space is, say, like a child variety, a space of all lines in C2. A space of all lines. This is a 2 complex dimensional space slope and y-intercept. A 2 complex dimensional space. Dimension 2. This is the family of lines themselves. The line, each point over here corresponds to the corresponding line that it represents. So this naturally maps, by the way, to C2, because this is the line itself in C2. Okay? But I don't want this to be my parameter space. I actually, because I'm talking about, I want to say that there are not triples of points on a given line. So I'm actually going to take a 3-fold fiber power of this collection of lines, which is going to map to C6. C2, C2, C2. So a point in this space, is a triple of points on a given line. A triple of points. And what do I want to say? I want to say that there are very few lines with 3 post-critically finite points. So I'm going to look at a space that consists of triples of lines. This is going to be my S. Okay. That's going to be my S. This is, by the way, now is a 5-dimensional space. This was dimension 2. This is dimension 3. And then I go up by 1 dimension for this fiber power each time. Complex dimension 5. The family of maps corresponds to the image under this map to C6. So the family of maps, so it's going to be a collection of maps, which is just parameterized by the coordinates. Okay, obviously I didn't need to write them all out. All right, so down over to 6. It's going to be a family of maps parameterized by these coordinates where this vector of C's is rho of some lambda for lambda and S. Okay, so I have a parameter space that corresponds to triples of points. I look at those points, those triples of points. Remember, they have 2 parameters. So this is a triple, even though it's 6 coordinates. I have a triple of points in C2 on a given line. That's going to be the parameter space, and that's the dynamical system. A family of quadratic polynomials. The x in question is going to be the point 0 in every coordinate. It's just the section over this base, which is 0 in every coordinate. And so to finish, let me just say, what is a preperiodic point of phi inside X? Phi is the family of products of quadratic polynomials. A preperiodic point means that 0, 0, 0, 0 is preperiodic. In other words, the parameters are all post-critically finite. So a point in X, again, I'll repeat this. A point in X is preperiodic for phi if and only if every single one of the parameters is post-critically finite. In other words, I have these triples of points on a given line which are all post-critically finite. And one thing what we have to prove then is to say that that cannot happen very much. And so what one does is say, well, that current vanishes. We know this if and only if in this special case. I don't have time to write it all down, but we know the if and only if in that special case. In these families of quadratic polynomials where you follow the critical point, we have a complete understanding of what the corresponding specials invariant subvarieties actually are. So with that, I finish. Sorry for going over by a lot.